So were there, yeah, we'll start off with, were there any questions? Anything you would like me to go over? Studying strategies, organic chemistry games you can play when studying with people, your colleagues. Okay, let's do some practice questions then. All right, so yes, I will. Right, we will do some, I'll do some practice questions, and then what we'll do is some studying strategies. Okay, so let's do, I'm gonna do, right, let's do this. Yes, I will. This is being recorded and I will post it on Top Hat later. Yes, I'll do that. Okay, let's see here. All right, so here's 4 questions. Each one of them has got something interesting going on in it. So take a couple seconds, or we'll take a minute or two, and try to, yeah, get the answers, I guess. So remember, each one of these has got some stereochemistry in some way associated with it. So that's the interesting part of this. I'll pause this so we're not sitting here listening to nothing for, okay. So while you're working on your answers, and whenever you've got your answers, just let me know through chat. One of the things that I would do is that I would take a alkene, some sort of relatively simple alkene, or you could start with like a cyclic one would be a good one to start with. Some good ones would be, say, like take a 6-membered ring and put some sort of group on it somewhere, like here. And with your alkene, particularly the cyclic ones are the best ones because there's no it's got a restricted conformation. So if there are any stereochemistry outcomes in the reaction, they are you have to draw them in your product. But what I would do is I would take this alkene, and it doesn't need to be this one, but just any simple one, and on it, do every single reaction that you can think of that we did with alkenes. And what you'll end up with, I'm going to sort of shrink this a little. And what you're going to end up with is a sort of a web of reactions. So if you had HBr, oh, this is the Markovnikov edition of HBr, I would have, say, this is my product. And with a lot of these reactions, there are two halves to it. So if one reaction adds H to the is a Markovnikov addition, there's typically one which is the anti-Markovnikov. So there's one reaction which does one thing and one reaction which does exactly the opposite. So I would build a little web of all of the various reactions from this same structure. And it gives you an idea. It's not like some people might say that that's a, what do you call those cards where you're study? Anyway, what I say is it's basically, this is your toolbox of organic chemistry and all the various reactions in your toolbox. And what we're going to do is flashcards. Yes, thank you. What we're going to do is that there is going to be one tool to do one thing, and there's going to be another tool to do like another thing. Every tool's got a purpose, right? So by the end of this course, we're going to have this big giant web of reactions which do a whole bunch of different things. Yeah, so that's one way to start, is just getting yourself familiar with the various reactions. Now, the reason why, say, HBr, oops, I just erased it. HBr in this reaction here, oops, in this reaction here, does the Markovnikov addition is because there's an intermediate in which we've got a positive charge, right? So the mechanism is that, and the mechanism for almost all of these reactions is the same. Like our double bond is the nucleophile, and where electrophiles are being added to it. So in the first step, we generate a carbocation, the most stable carbocation, and then the bromide that comes in and attacks, and that gives us our final product. I'm actually going to erase this little carbon here just to make it a little bit easier. So, and for each one of these reactions, when you sort of make your little map, just try to remember exactly what the mechanism was as to why we did that. So now, HBr does the Markovnikov. The one which does the anti-Markovnikov, of course, is going to be this one over here when we've got the, it's a bit too dark. We've got that peroxide with it as well. And that's because the mechanism's slightly different, but the product that we're going to have results from the most stable radical. So I guess I should put a BR here. And then this is going to form our final product C, based upon the fact that, so when our bromide radical, oops, this is got the wrong compound here. But anyway, so the first thing I would do is start a little web of reactions, starting from some simple alkene. And I would draw a tri-substituted one, just because it allows for all of the various stereochemistry things associated with each reaction. So does anyone have an answer do people have an answer for A? Okay, so if you don't have an answer for A, D2 is basically like H2, except it's the deuterium isotope of hydrogen. And the reason why I've done this is because we are adding D2 across this double bond. And the thing to remember is that the deuterium is basically absorbed onto the surface of the metal. So they will add on the same side. So our product should be either, I'll put the two Ds forward, put a methyl group back, or, and you don't need to draw both, you just need to draw one. You could have the two deuteriums back. So as long as the two deuteriums go on the same side, perfect. That's so when we're doing the hydrogenation reaction, this was dependent upon the two being on the surface of the metal. So they're added what we would call syn. So they're on the same side. So same side. And the other thing, which there was another thing about the hydrogenation reaction on a double bond, was that because the alkene has to approach the surface of the metal to react, if you've got something which is big, like a really big group on one side, so if we had like a big sort of tert-butyl group here, or isopropyl group there, if we were adding D2, palladium on carbon, we would expect that the deuteriums would be on the opposite side. So once you like the other, okay, once you've made your little map of reactions with D2, then, I mean, sorry, your reactions with an alkene, gosh, it's Monday, but it's Thursday. Then you can actually quiz all of your friends, right? You can just draw any alkyne and say, okay, what is the product of this reaction? And you will already know what it is. So it's like almost a game. But we'll talk about that in a second. Okay, so there were three reactions which had very similar outcomes associated with them. And they all had some group here, which I'll call Y, and it had a positive charge. Call this R. And a nucleophile is going to come in and attack this. And because it's this three-membered ring with a positive charge, the nucleophile would come in on the opposite side. So it's going to come in on the opposite side. And the other thing which was interesting is that in a couple of the cases, it would always attack the carbon, which was the most substituted. If it was in the case of, say, water. But those three reactions, the three things, the three structures were as follows. The bromonium, the mercurium, And last but not least, an epoxide that had been protonated. So protonated epoxide. So the nice thing is that all three of these behaved in a similar way. So our next question was over here was reaction B. And so we have our mercury diacetate. Remember, the acetate's a leaving group. So the double bond is going to attack the mercury. One of the acetate groups is going to leave, and then the mercurium is going to form that three-membered, that three-atom, the cyclic structure. So the intermediate here for B is going to be we've got a methyl group here, a methyl group here, and we've got an ethyl group over here. And in our solution, we've got some water. Water. So our water is going to attack the most substituted carbon. That's going to open up. And so our product for B, this is only for the oxymercuration reaction. Remember, there was two steps. One was mercury diacetate, water, THF. The second step was the sodium borohydride. I purposely left the sodium borohydride out of here because the first step product is far more interesting than the final product. So the product we're going to have when we do this, is that if this opens up, if I'm going to just draw this from the perspective that I had on the page, OH. And the ethyl would be over here. This would be forward H. So the key point here is that these two groups, the mercury and the hydroxyl group, are anti. And so that's the first thing. The second thing is the OH is on the more substituted, spelling wrong today, the more substituted carbon. So this is a Markovnikov addition. So if we're going to draw B, our product is going to look like this. I'll draw the OH group forward just for the sake of it. And I'll draw our mercury. I'll draw our mercury. I don't like that. Like that. It's going to be on the opposite side. The so the key point is that these two groups are on opposite sides. So if you keep the perspective of your alkene the same, so if we had, someone's got a question. Yeah, so there's two different products. Like there's two enantiomers here, really. There's this product or it's the other one where you've got the mercury forward and the OH backwards. So there's two different possible, the two enantiomers are the two possible products here. But the key point is that the two of them are on opposite sides. So how many people got the A right and B right, or one of the two of them right? Excellent. All right. So be hydrogen bromide and a peroxide of some type. So in this reaction here, this is the radical reaction. I guess I'm going to have to move down a bit. So much like when HBr is adding Markovnikov to a double bond, when you add the peroxides, it adds anti-Markovnikov. But the reason it's anti is very similar. So in the case of the Markovnikov, it was because, as I said before, we're generating the most stable carbocation. In the case of the radical reaction, bromide is going to add to the double bond, but when it does, go down here. There's two possible ways it could add. We could add it to the first, we'll add it to this carbon, and this will be our product. The other possibility is that it could add to the most substituted carbon. We'll draw this in green. Now, the difference between the two is that in the case of this was a tertiary radical, and the green one is a secondary radical. So radical stability, this matched carbocation stability. So tertiary are more stable than secondary, which are more stable than primary. And if you have a radical that is stabilized by resonance, it's more stable than the tertiary. So remember, resonance provides stability. So if we had a system where, oh yeah, that's a good point. So radical stability it parallels carbocation stability. So the intermediate, this tertiary radical would be lower in energy, so it would be easier to form. So that's why you get the product. So here, our product would look like this. And there is no stereochemistry in this reaction because the double bond's flat, so you'd end up making it would be a racemate because the bromine could add on each side and it would do it 50% of the time from each place. So this is basically one product here, which would be a racemate. The positive enantiomer and the negative, plus and the minus. So this is the complementary reaction to the HBr with no peroxides. So if we had HBr and then ROOR, then our product would look like this. So whenever I'm doing a little web, I'd always make sure that I've got the two complementary reactions sort of side by side. And that's going to, I think it helps. I don't know why, but I just think that when you see the two sides, like it's like a coin, right? Two sides of the same coin, heads or tails. I don't know. Now, this last reaction was a design, or what we'd call a designer reaction, the osmium and NMO. This was a specific reaction that doesn't really have a partner associated with it. It was a way of making adding hydroxyl groups to each carbon. So it was what we call a dihydroxylation. I'll draw this up. Draw that back just so it goes back. So there was basically three sort of reactions that were sort of off on their own. One would be the osmium tetroxide reaction, OSO4 NMO. That would be one. The second one I would say would be the ozone one, ozone and then triphenylphosphine. And the third one I would say would be the cyclopropanation. So the carbene reaction. So making a, for the lack of a better word, making the triangle. So remember, this was diiodomethane, copper, and zinc in ethanol, or sorry, diethyl ether. So the key part for the cyclopropanation was that it was a stereospecific reaction. If you had a trans double bond, you would make a trans epoxide, so to speak. So not epoxide, cyclopropane. I guess the formation of an epoxide could be added to this list, but because the epoxide has got that, it's very similar to the bromonium ion and the mercurium ion with regard to how you open it up. I sort of, it's, I guess, actually, it is in a way related to the osmium tetroxide. So this would be 1A and 1B. This would be the MCPBA to make the epoxide. And then you can open it up to make the trans. So if you make this, if you use base like hydroxide, you would make the trans diol. So yeah, I guess the osmium tetroxide and the MCPBA, the two-step MCPBA protocol, are complementary because one makes a cis diol, the other one makes a trans diol. So one of the things I would do would be to do, and it's going to take up a lot of space actually, to make a, just choose a alkene and do all of the various reactions off of it. And as you go through all of the notes and stuff and do them, you'll see that there's two reactions will be complementary. So put them side by side. And then you can basically just make up questions yourself using any old double bond and just putting some things there like Br2 CHCl2, call this A. And then let's do this one. NBS, water, and DMSO, B. And when you do B, you're going to see something which is interesting, which okay, yes, we can do that. Okay, and then let's do another one with, let's see. So try each of these three reactions and see which products you end up making. So remember NBS, which is the N-bromosuccinimide, it's a source of both bromine plus and bromine radical. And it's used because it's a nice crystalline solid, so it's easy to weigh and that sort of thing. The bromine, molecular bromine, is a red liquid, which is quite pretty, but it's very dense. And sometimes, particularly if you're using small quantities of it, and you need a precise volume, it can be slightly problematic. So it's sometimes just easier to use NBS. Plus, it fumes a bit. If you don't like the breathing in bromine, then it can be a bit of a problem. Okay, so remember, in both A and B here, there's going to be an intermediate that we're interested in, which is going to basically dictate the course of the reaction. And that is, we are going to have a bromonium ion. So what if your double bond is drawn as a zigzag? Make sure you draw this as a zigzag. Now, in the case of product A, so the bromide is now going to attack, and it can basically attack two carbons, right? It could attack carbon A, or it could attack carbon B. But and it's always going to attack on the opposite side, because that big bromonium is blocking the top side, so it has to attack from the opposite side. So if it goes through route A here, our product is going to be, this bromine's going to be back, and this bromine's going to be forward. So this is A. If it goes through route B, it's going to make this. Bromine's going to be back. This one's going to be forward. So this would be B. So what's the relationship between little a and little b here? What is their relationship? Stereochemically. They are enantiomers, right? So if they're so these two are enantiomers. So there's opposite stereocenter at each chiral carbon. They're enantiomers. So if the two products are enantiomers, we can just draw one of them and we don't care about the other one. It's just, so either one of these answers is correct because they're both enantiomers. Now, if we look at question B, so we're going to have the same intermediate. Plus. So there's a couple electrons there. And now we've got water, which is going to come in and attack. Oops, extra set of lone pairs there. And so which carbon is the water supposed to attack? in just in general sense. So if you've got a bromonium ion and you've got a water as your nucleophile, it's going to attack the more substituted carbon, right? So in this case here, if I make this A and I make this B, which carbon's the most substituted carbon? Right, they're the same. So let's draw our two products here. So let's have this guy attack here, that go up. So this is product A. Remember, there is an intermediate where this water is protonated here, but it gets lost during the course of the reaction, that proton. So I'm not going to go through that step. Okay, that's the product if we attack carbon A. If we attack carbon B, when this goes up, our product's going to look like this. Remember, the OH group is on the opposite side of the bromine. Okay, now, what is the relationship between these two molecules? Yes, Kat. They are diastereomers, right? Okay, so these two things are diastereomers. So we've got they're both okay. Both products, the OH group and the bromine are on opposite sides. We've kept our lines consistent, the zigzag, but these are diastereomers. Diastereomers. Which one of these is going to be the major product? Well, I don't know which one's going to be the major product. It's going to probably be a mixture of the two. And so this question, I probably wouldn't ask because we're forming two different diastereomers, two products. I don't know which one's the major product. And if part of the interest, so when I said, well, where's the water going to attack? Which type of carbon does it attack preferentially? And someone said, well, it attacks the most substituted carbon. That's the key point of the question, right? So there's a couple of key points. The first key point is that the two groups are on opposite sides, so you make the bromonium. But the second point is that the water attacks the more substituted carbon. So if I'm going to ask a question with like NBS and water, for sure I'm going to have one of the two carbons being more substituted than the other, because it's so this is sort of why I said when you're doing, if you're making a little map at the start, make sure that one of the carbons has more substituents on it than the other. So if there's any Markovnikov or anti-Markovnikov addition going on, you can see it. So yeah, this type of question here, I'm not going to ask it on a di-substituted or a trans or a cis double bond, because there's two possible diastereomers that would form and we wouldn't know which one would be the major one. So, but it's still it's good practice, because when you do it, you'll see that, there'd be two possible products there. Now, which one's going to be the one which forms? So I probably won't ask that type of question. But third question here, I do have a double bond. So if I do have a double bond, which is a double bond which is di-substituted, and so in an instance like this, Markovnikov or anti-Markovnikov isn't actually, okay, I'll ask this question in a second. But there's something interesting going on here. There was a couple of reactions in which the thing which was important is we would say that they were stereo specific. So if you have trans at the start, you end up with trans at the end. If you have cis at the start, you end up with cis at the end. And the ones which were really important with that are the epoxide and the cyclopropane. So this third question is the carbene question. So carbenes, I'll draw it like this just for the sake of it. It was this odd molecule which has got effectively it's carbon negative, carbon positive in a CH2. And in inorganic chemistry, they're quite common. And they're usually the way that this carbon minus and carbon plus is it's usually attached to a metal of some type to help stabilize it and all that sort of fun stuff. But the way that this works is that this will attack the empty orbital, and so that means that there's a developing positive charge on the other carbon, and then the electrons here come down to that delta plus. And so if you start with a trans, make this go forward, make this go backward, they will keep that, it'll still be trans at the end. Yeah, I don't know what else to really say about that. So if I ask a carbene question, it's probably just to make sure that people, if it's trans, keep it trans. If it's cis, keep it cis. There's a surprising number of natural products that have cyclopropanes in them, and considerable amount of research has gone into making one enantiomer over the other. Like you can do cyclopropanations where you make the propane sticking up and not sticking down. And there's a famous chemist at the University of Montreal who did this sort of stuff at the start of their career. So it's really interesting. So it's one of those, because the reaction is very similar to the epoxide, it's probably why it's included in quite a few of the textbooks for second year chemistry. But what we do with the cyclopropane after this, in most instances, there isn't a whole lot to do with it, right? But a lot of the other reactions, there's a whole bunch of other things we can do about it. So it's interesting that it's basically included in a lot of our text for this chapter. Yes, the test will have multiple choice questions or matching questions or sorting questions or click on, I don't think we can do click on target questions, unfortunately. Okay, now, what you can do is, as I said, make a little map. We've got double bonds, we've got triple bonds. Make your little web of reactions. Make a little mini test and quiz your friends. The other thing which is fun to do is, which we haven't really gone over, you'll notice the last question on the last midterm was something like, you start with, well, actually, so here's our Markovnikov addition. Here's our anti-Markovnikov addition. Let's do methyl. Something like this. there are different ways, like if we think about um, our elimination reactions, there's a way to go back this way, and there's a way to go over here through E2 eliminations, right? And so there's a way to go back the way we came, and then there's a way to go over here through E2. And it depends upon, is it a small base or is it a bulky base, right? The bulky base gives you the least substituted product, and the small base gives you the more substituted product. So that's another thing that we're going to end up doing is, okay, from this we can make all these different products, and what do we do from here? Like, what can this be used for in the future? So we're going to make a giant web of reactions. And the fun part is, and this is the fun part of organic chemistry, this is the thing which at least got me interested in it, is that you can start off with something which is relatively simple, like this, and you can make something which is relatively complex, like, say, so you can start here, and through a series of steps, make something which looks really nothing like it, right? And this is what we would call synthesis. So the last question on the posted midterm from a couple of years ago was a synthesis question, and it's about developing, like, through a series of reactions, something which is quite complex from something which is really simple. And the way you would do this is that, like, if you're looking at like a triple bond, and then you're looking at, we've got an epoxide in this other thing, how do I make this? It's the easiest way to work on these sort of things isn't to work from the start, but to work from the end and then work your way backwards to the start. And it can be fun. It can be a fun little game. So this is another way to study with your friends, is to if you've got if you make your little web of reactions. So let's pretend I've got a double bond here, and so there's a question, is synthesis on the test? Not in the sense of quite like this, but if you look at the assignment, I've done a couple of synthesis sort of questions, like having some sort of starting material, have some reaction conditions, have a product A, and then some more reaction conditions and having a product B, that type of thing. So it's not quite the same, but it's similar. It's like some people call these sort of things roadmaps, reaction roadmap. But they're less creative because I've decided what the reactions are. It's more creative when you can do it yourself. So if you, let me erase this a bit. So if you've got a friend who's in this class, or someone you want to study with, one of the things you can do is that, okay, I'm going to do a reaction, and let's see, what's a good one? I'm going to do it with triple bonds because triple bonds, we've got more chemistry with triple bonds, but let's say we've got this. Okay, what am I going to do with this triple bond? Okay, I'm going to do a LDA reaction, one LDA, two ethyl bromide. Okay, so that's going to make our methyl. Then what reaction do I want to do? I want to do a reducing metal reduction to give me the trans double bond. Then what do I want to do? Then I want to do a, stop that. I want to do an osmium reaction, OSO4, NMO. The first step, second step, the aqueous workup. And this gives me a product which looks like this: methyl, ethyl, and the two hydroxyl groups. And they're both cis. Oh my God, it's 10 o'clock. Anyway, sorry. Yeah, the test will be like last term. It's all going to be multiple choice. Sorry, I totally lost track of time. Someone should have mentioned it. Anyway, if you've done this yourself, then just give this to your friend and say, okay, start with this and make this. And it's a nice way of basically studying all the various reactions. This can almost be like a game. And you only have to do a couple steps. And it's going to give you a sense of what are some of the possibilities. Anyway, I apologize for going late. If you got tests, good luck on them. And if you've got any questions, let me know. I'll post the answers to the old midterm, and this test will be very similar to the ones we did last term. So mainly multiple choice or matching and that sort of stuff. Okay, sorry about that. Alrighty.